Hi, I'm Wes Porter, an Extension Specialist here at University of Georgia. I'm covered Precision Ag and Irrigation from the Extension side, and today the topic that we're going to be covering specifically is unmanned aerial systems or unmanned aerial vehicles. And so to my left here on this table, we've got a wide array of different types of systems, and I call these unmanned aerial systems because each one of them is more than just a vehicle. If we just had what's commonly known as a drone or an unmanned aerial vehicle without a sensor or a camera on it, we would call it just a vehicle. But these are unmanned aerial systems that we're sitting here. And I'm going to talk you through some of them, the usages of them, how we use them in ag, how we use them for research. So first, sitting just to my left, this bigger system is a fixed wing, and you notice it looks kind of like an airplane. So this one is actually a little bit unique that it takes off sort of like a rocket and then it corrects itself once it gets in the sky. If we move to the left a little bit, we have three quadcopters over there. We have a DJI and then two 3DR solos. And so I just wanted to show you two different types of quadcopters versus a fixed wing. And while we're talking about those, I really want to go into detail the difference between when we would want to use a fixed wing like this and when we want to use a quadcopter. And so when we start looking at that, a fixed wing has a much longer battery life. We can cover a lot more acreages with that, but we usually fly at a much higher altitude. The reason it has a longer battery life is because, one, it's a little bit bigger platform. Typically it's a little bit lighter because this one's mainly made of foam. But on top of that, when it's up in the air, just like an airplane, this is how we need to relate those, it actually does a lot of gliding when it's in the air. And so it can save battery life when it's in the air and actually capturing images by gliding across the field. And so we're able to cover, somewhere in the 30 to 60 minute flight times on some of these, whereas with our quadcopters, we're sometimes only able to really fly for in the 15 to 30 minute range. And so we have to think about with a quadcopter, the big difference and the reason we use those is they are like a helicopter. They're having to hover the entire time. And so while they're hovering, they're using energy from that battery and draining it down. So again, we don't have the long flight times, about a 20-minute flight on average, but these have a very specific use when we're starting to do research because we can fly a lot lower, a lot closer, and kind of track objects with those. Unlike with a fixed wing, when we're way up in the air around that 300 to 400 foot ceiling, these we can fly even down as close to 15, 20 foot above the ground level and actually see what's going on the ground, have extremely high resolution photos from those. So that's the main two differences between these two systems. As we start to talk through the systems themselves, I want to talk about different sensors that are installed on each one of them. The fixed wing and the system in the middle over there both have a multispectral camera on it. And when we start talking about multispectral, what that is that's bands like near infrared, infrared, red, green, and blue. And we use multispectral to really look at plant health or estimations of plant biomass. It's a little bit different than just taking normal images of the of whatever we're looking at. I'm referring to plants a lot of times because that's usually what we're flying over, but we can fly over and take images of a lot of other things. The white DJI right here just to my left, the quadcopter I'm pointing to, has just a standard RGB camera on it. And so a lot of times this is an integrated camera that's on this system, but a lot of times we'll mount just a GoPro camera. A lot of people are familiar with those, the kind of GoPro tough cameras on these systems, and that gives us the availability to do one of two things. We can either take single images from this while we're up flying, we can take multiple images as we fly, stitch those together, or we can take videos from this system. And so those again are just going to be, we call that an RGB camera. That's red, green, blue. That's the same as the camera on your phone, the same as a point and shoot camera, any of that. Again, it's a lot of times a GoPro on that one. So you can imagine we're kind of limited from the scientific perspective on what we're able to do with just a standard camera versus what we're able to do with that multispectral camera. And then if we move all the way to the far edge of the table over there, and you notice that camera on the bottom of that system is much larger, and there's a bundle of wires kind of hanging out from them. Well, that's a thermal camera. So thermal cameras are basically looking at heat signatures. That's the most simple way to look at it. And so we have specific applications for this in agriculture. One, if we're looking at plant health, plant disease, potentially irrigation scheduling, those types of systems can pick up quote unquote hot spots in the field where the plant's not as healthy and not able to transpire as fast, or if there's a lack of soil moisture where the plant can't transpire, can't pull that soil moisture up through, we can identify some of those hot spots with a thermal camera. Outside of ag, industry uses thermal cameras a lot of times to identify energy issues on buildings and other places because we see we have energy leakages out from that thermal area. But you notice that's a different retrofit. A lot of the thermal cameras, it's harder sometimes to find some of those fully integrated, and so we had to do an integration kit on this system to make sure we were ready to fly and go. And I would also point out When we talk about flight time and we talk about using these, you notice that is the largest camera on any of these systems. It's going to weigh more. And so the same way, since this system's having to hover the whole time and it's carrying a heavier payload or a heavier camera under there, that means our flight time is going to be much shorter. So we have to really consider some of that when we're setting up what areas we want to fly and what we want to do, really specifically with these quadcopters, and start thinking about how long that battery is going to last and make sure, can we complete this flight, or do we need to break it into multiple flights, or is there something else we need to decide? Do we need to go back and think about using a fixed wing depending on field size or something of the such? So that gives you kind of a broad view of just UAVs, different sensors, different UAV types, you know, fixed wing and quadcopter. So with that, we're going to move on in just a second to flight planning and some of the other actual data processing and everything. Now we're going to discuss flight planning, and so most of the UAVs come with a type of remote that does manual control with those. In addition to the manual remote, a lot of times we can add a cell phone, add a tablet, or some other control system to this remote, and it actually has an application on it that talks back to the unmanned aerial system and does an automatic flight control. So it really depends on what your goal with the system is. If you're just wanting to fly it for a hobby and you don't need a ton of automatic control with it, generally you'll just use the remote itself and you'll manually fly the system. If you're wanting to do research, or you have defined paths that you want that system to fly along, then you'll want to integrate a smartphone, a tablet, or some other kind of control system along with the pairing app with your unmanned aerial system to make sure you can set up proper flight plans, follow those, and collect the data that you need to collect from them. One thing you want to think about when you're setting those up is usually put in the type of sensor you're using, the altitude that you're flying at, and it really takes some of the guesswork out of the flight planning for you. It sets up, once you draw a boundary around the area you want to fly, it gives you an estimated flight time, shows you the estimated path that system is going to fly, and then lets you adjust that to best meet what you want to be able to do for that particular operation. And this is going to change by sensor that's on it. If you did one flight with that RGB camera versus a flight with a multispectral, it's going to have to fly at two different altitudes, and the number of passes it's going to make is going to change. And then because of that, it gives you an estimated flight time, and we've talked about that already with the battery. You need to look at that estimated flight time and make sure it's within a reasonable amount for you to be able to do the entire flight without the system running out of battery, because the software would not necessarily know how long your battery is going to last for that particular system based on payload, based on battery age, and a few other things. So these are just some things to consider about flight planning. After you've done the flights, the thing we really have to look at, and probably some of the hardest part of unmanned aerial systems, is when we get the images. What do we do with those? And so depending on our goal, what we're doing, and where we're at, that's where we have to make that decision. Usually if we're using it just for hobby use and we have some photos or a video on it, that's not very hard to handle. It can be very large files. As you know, today when we create videos with our phones or with video cameras, they're high resolution, they are larger files. So you need to make sure you have a way to move those from the system to your computer or wherever you're going to show those. But if you start looking at, you're trying to stitch images together, you're getting some high resolution research style data, we create massive amounts of data like that. There's some stitching software out there, some free softwares, but usually one of the more popular softwares a lot of people use is Pix4D. For example, we have a license to that software here, which it allows us to stitch all the images that we've collected from a field together into one big image that's high resolution, and then we use that one big image to start doing some of our analysis with in a GIS software. And so some of this process of image stitching can take hours, but it can take up to days when we look at this. And so that's some of the issues when we start thinking about doing long flights and collecting a lot of data out there, is we also have to keep in mind how long it's going to take us to stitch these images together and how big they're going to be. One example of a flight that we did recently, we covered 140 acres with that multispectral camera that we talked about earlier, created 2,830 images. And so that's a lot of images for 140 acres. The associated files were just near 6,000 files for that, and that was 7.2 gigabytes of data. And you might be saying, okay, what's 7.2 gigabytes of data? What does that really mean? To maybe bring it into perspective for you, if you think about downloading songs on your phone, a typical song is about 0.005 gigabytes of data, or 5,000ths of a gigabyte. Now that's about 1,500 songs to equal that flight time. Or if we want to talk about HD movies, because we download those on tablets and phones now to watch, HD movie is about 4.5 gigabytes. So this flight created 1.5 movies. So keep that in mind as we're flying these systems and some of the stuff we're doing, the massive amounts of data that we're dealing with, and where we're having to store it, how we're having to handle it, and the time it takes to process it. And finally, we're going to discuss some issues with utilizing UAVs and doing some of this work. You know, they seem fun, they're cool toys, they're really good research tools. You know, there's a lot of things that we can do with them. And if you kind of picked up through some of my other talk, I alluded to some of the issues while we're using them. And there's some things you need to be aware of before you just run out to the store and buy one and say, hey, I'm going to start doing this work with it. One of them is battery life on the systems. Again, depending on the type of unmanned aerial system you buy, the battery life's going to be anywhere from 20 to 30 minutes up to an hour, and that's the difference between a quadcopter and a fixed wing. In addition to battery life, we start talking about when we start collecting all this data, what do we do with it, or all these images? You know, and you need to have a defined plan. If we're talking about it from the research perspective, we have a lot of external hard drives and a lot of storage space we have to put all this data on. We also have to have a way to process all this data, and the time it takes to process it really requires a high-end computer. So just a standard laptop from Best Buy or from Staples or somewhere is not going to do what you need to do. You need to have a really, really good computer, more like a supercomputer, to process this in a timely fashion and so that it can run it adequately. And then on top of that, once we get some of these maps and some of this data stitched together, we've got to understand what we want to do with this data. It's not just a magic, we've got a pretty map here and then now we know exactly what's wrong with the plant or what's wrong with that crop field. We really have to still go out to the field and do some scouting and figure out why the plants are healthy or warmer or got issues in certain areas, and why some of the plants are not so healthy or have some other issues going on. So then there's a correlation between what issue are we trying to detect and what are we seeing from the unmanned aerial system. And so that's where the research really starts coming together, and there's a lot more time and effort that has to go into that too. And then we also have to kind of understand the value of these systems, and I don't think that's something that anybody's really figured out yet. Of course, there's a price for the system, but if we want to use one on a commercial scale, what's it really worth? How do we charge to use it? You know, and what's kind of a price structure there that we can get any return on it, or you know, or charge somebody to come out and fly their field. We're still trying to get some of that stuff determined now. So again, I just want to make you aware that they're not just an end-all do-all. For a little while everybody thought that they were kind of a solve-all, but there are some issues you need to consider before you just jump headlong into using these. So thank you for your time and attention today, and hopefully this kind of gave you a little bit of information on unmanned aerial systems in agriculture and helped you learn a little bit about, if you're interested in them, about what directions you need to take and you know, kind of where to go with them.